Hello everyone, my name is Florian Brugalla. This is a DSP coding tutorial and today we are coding a procedural wavetable LFO. But before we are starting with that, let me introduce you to the problem. LFOs typically have a rate that can either be in temposync or in hertz. Sometimes also seconds or milliseconds, but that's basically interchangeable with hertz. Around 1 month ago, I made a little poll in which I asked you all what kind of LFO rates you enjoy more. Do you like temposync values more or values in hertz or milliseconds, or no preference? And we can see two very interesting things in this poll. The first thing that we can observe here is that the amount of people liking temposync values is pretty much the same as the amount of people who like hertz or milliseconds values. Of course, with barely 50 votes, it's not like the most representative poll of all time, but I think we can still kind of see that there is a certain trend. And the second thing, which is even more interesting in my opinion, is that the amount of people who have no clear preference for one of these is very low, only 10%. And we can of course just ask the question why that is the case. Since I want to go somewhere with that, I can tell you that my personal assumption is temposync values and the other values, which are often hertz or milliseconds, actually imply different perspectives on how making music should be. An LFO typically has a speed, but that's not all that an LFO has. An LFO also has phase. In this image, for example, you can see that there is one wave cycle of an LFO and there is a parameter where you can set the phase of the LFO, and this parameter defines the start of the cycle. So if it was here, then we would always start at the beginning of the wave cycle. If it was here, then we would start at the point where the value goes down into the negative numbers, and we can also start at other points than the zero crossings. And you might think that it kind of makes no sense to even differentiate between different phases because it is just an LFO and it just keeps on running. But if you imagine that you want to have a very certain phase at a very certain moment in time, then you can maybe have that visualized better in this way, where you can see that depending on where your start phase is, you get a different shape out of the LFO for the upcoming wave cycle. Check this out, I prepared a PowerPoint presentation for this video. Turn up. So now we are talking about an LFO's phase, and specifically about the phase when the rate is being in temposync during playback. So as you all probably know, temposync values are the ones that relate to certain beats, like in this case a quarter note, a triad, a dotted quarter note or half note, stuff like that. And the temposync phase depends on the rate, the project position in quarter notes and the BPM. I'm saying that very specifically that it's only during playback, because when there is no playback, the project position doesn't move, but the LFO still has to keep on going. So even when temposync is enabled, all these dependencies are not true anymore when the playback is turned off. So this is let's call it deterministic LFO phase, because whenever you come around at the same project position again, for example because you are looping the project, it will sound exactly the same because you're running over the same phase again. That's why I define deterministic as consistently loopable. But the problem, and now we're talking more in terms of musical value, is that it can be too gritty sometimes, you know, because you have this very locked to the grid sound. Yeah, you might not want that. And that's why there are also other types of rates. These can be rates in hertz or in seconds or in milliseconds or any other value that is not directly related to a musical beat. In most LFOs, the phase depends on nothing in this mode, which is why I call it non-deterministic. It is chaotically loopable. When you come across the same point over and over again in the project, it will always sound a little bit different, give you a new perspective. And this has the musical value of being a little bit more off-grid. I want to talk about the mindset of the studio musician right now. When you are performing as a studio musician, you're performing the music with much precision, because the goal is to manifest the music into a physical form at the end. If it's a FLAC file or a record, it doesn't matter. It must be on some medium where it can be played back and where it can live on forever. In this process, you are making really careful decisions. You are listening very carefully to the sound, and with all this critical thinking in the process, you want to always know exactly what's going on. You are setting all of the effects and mixer tracks and equalizers and stuff like that to very certain settings, and you always want want these settings to sound precisely the same. You are arranging all of that stuff. You are basically the orchestrator of a new little musical world. And if that's your way of thinking, then you might tend to like the temposync values of an LFO a little bit more, because you can really trust them to always sound the same every time you export the project. And then there is the mindset of the musician. In a perfect world, this would be the same mindset as the one that you have in the studio. But more realistically speaking, there are just people who feel more comfortable in the studio and some people feel more comfortable on stage. And these stage people don't care a lot about the temposync values in the DAW, they just care to dial in the correct tempo. And they know which tempo they want. Without even thinking of that, they are setting up all of the effects they need, and it doesn't really matter if it always fits perfectly, it will just somehow create the vibe that they are going for. Musicianship in this traditional sense is really important, and that's why there are still LFOs in hertz, in milliseconds or seconds, even though it seems like it's a less sophisticated way of looking at speed in a DAW context sometimes. Alright, I just freestyled some vocals. Let me apply the vibrato to these tutorial vocals. And I deliberately made them sound very flat with Melodyne so that I can craft my own vibrato in Nell. So let's go to the LFO modulator and try to find a good setting. Let me apply the vibrato to these tutorial vocals. Okay, great, but now it will sound a little bit differently every time when I repeat the section. Can you hear that? It always has a little bit of a different flavor. So now I will actually load a more recent build of the plugin Nell that already has the procedural LFO that I'm going to present. And you can hear that it always sounds exactly the same when I'm repeating the sound. And the plugin looks better as well. So now we can actually use the phase parameter to find a good phase for each line, which would work like this. Let me apply the vibrato. I made an automation for the phase, and now I can just decide for a start phase that I like for this section. And I can decide for a different start section for the second line. Trying different start phases might be a very subtle effect on a sine wave, but you can of course also think in different wavetables. Like here we have a Weierstrass sine wave that gets more complex the more you dial it in, and suddenly each point in the phase actually has a lot of a difference, especially if you turn down the rate a lot so that it cycles through this whole thing much slower. If we want to talk about the procedural LFO, we have to talk about procedurality itself before. I always find it to be one of the most exciting concepts of modern gaming, because games like No Man's Sky and Minecraft have really pushed it to its limits. There, the whole terrain and also a lot of other parts of the game are procedurally generated, which means that there is some sort of noise in the background, mostly pollen noise or something of that sort, and every specific point in the map relates to a specific phase in this noise segment, and that's why it on the one hand appears random and on the other hand always gives you the same exact thing when you return to the same place in the map. We can just apply the same idea to an LFO, of course, where each point in time maps to a specific phase. And I drew this little image for you to showcase what I mean. I drew it in temposync rates though, to make it a little bit easier to understand. Here you can clearly see it visualized that as long as your start phase is beginning here, you will always have this particular wave cycle mapped on a quarter note of the beat. And you can do the same for an LFO rate of 1/2 and it will just be twice as long. And the idea is just to have the same thing for LFOs in hertz, seconds or milliseconds or whatever. And then of course it will not always be as clear where the start phase actually is. On something like bar number 5, it will not always be just 0 unless you mess with the phase and really listen to it, but at least you have the control over where you want it to be. So here we are in the actual code base of this plugin. And now we navigate into the modulator section, and I must say I'm currently in a very old commit of this project. It's like 2 years ago or something. Okay, here we have the LFO. So let's now search for the part where I deal with the phase when the LFO is set to Hertz. And you can see already in the way I'm naming the variables here that when it's set to Hertz, I already assume that it's also running freely. So here in my set parameters function, I'm updating the rate if it's the different value. And then I'm giving the phasors, there are apparently multiple phasors, the new increment value by dividing the rate free parameter with the sample rate. And this is the processing function here. If we are currently in temposync and it can be synced, which means there is a playhead, then we get the current position and calculate the temposync stuff. Or if this is not the case, which would mean that we are currently free running, then we just synthesize the phase, which just means we let the phaser run and we put it into a buffer. So as you can see, there is just literally no handling about phase at all when there is no temposync. And that's the case in most plugins LFOs out there. That's why I always assumed it has to work like that. But as I said before, why would we always put all that effort into the temposync rate but not treat the Hertz rate the same? I'm not sure why people never thought about that, or at least not a lot of people. I know some plugins implement that a little bit, at least. We'll come to that later. So now it's time to go back to the latest branch of this plugin. And now everything looks a little bit different, and I can show you what's going on in the new LFO. So let's go to the part of the code where I update the speed. And you can see the speed is still defined as the rate in Hertz divided by the sample rate. But now in update position, I also check if there is tempo sync or not. And if it's not, then it's not just free running anymore, but it's defined as PPQ position divided by beats per second times rate in Hertz. So as you can see now, the rate in Hertz, the beats per second and the PPQ position all have a certain influence on this value. And if you are wondering why you don't see the playback position here, that's just because in the function that actually calls update position, I already checked for is playing before. And if it's not playing, then it will be free running no matter if it's tempo sync or in Hertz. If you like this video so far and want to see more of that, give me a like and a subscribe. Also, consider sharing this video with your friends and family who are surely interested in DSP, audio programming and music production as well. Alright, so let's talk about the LFO phases dependencies. As you have seen, the phase always relates to the rate, the project position in quarter notes, PPQ, and the BPM. And well, also kinda the playback. But wouldn't that kinda mean that there is always a huge discontinuity in the signal whenever you are modulating one of these? Because, you know, they have to work together, and every time you are modulating one, it would just be noise, I guess? Let's find out. And we can actually find that out very easily by just instantiating a bitwig filter and applying a bitwig LFO to it. Set it to unipolar and then attach it to the cutoff and listen to the sound. Let me apply the vibrato. So this is currently free running Hertz. Always sounds a little bit different when you start playing it back, but it has a drop down menu where you can set it to sync. Now you can hear it's still in Hertz, but it resets. So it is the deterministic procedural LFO, as I like to call it. Now let's modulate the rate. Let me apply the vibrato. And just as I thought, it just sounds very crunchy. Let's try BPM modulations. Let me apply the vibrato. That also had instantaneous transitions. Let's try looping. That also was a very instantaneous jump back to the phase where it was before. So you can see this implementation has no regard for transitioning between the values. It is not very modulatable. So let's instead check out how it's done in Vital's flanger itself. This flanger can also be set to tempo sync values or in seconds, which, as I said before, is interchangeable with Hertz. What happens if we modulate that? Let me apply the vibrato to these tutorial vocals. And that, for some reason, works, even though this is also a procedural LFO. Check this out. So yeah, this definitely always resets to the point in time where it is locked to, and that makes it deterministic, but it sounds less crunchy on modulation, and the reason for that is because it is crossfaded. So my concept of crossfading LFOs worked a little bit like this. I was thinking something like, okay, I have an LFO and it has a rate and a phase, but it can't do any crossfading on its own, so I let it be owned by a more high level LFO, which is called LFO 2 here, and it has 2 of these LFOs, and every time there is a rate change, it triggers a crossfade between these LFOs. But there are also other things that can initiate a crossfade, for example BPM changes. So I added another layer to this hierarchy where an LFO has 2 of these LFOs that were the high level LFO before, but now it's the low level LFO of this one, and that always crossfades when there is a BPM change. I thought that this would be a very smart idea because it means that there can be still a crossfade running on the rate changes while the BPM wants to initiate its own crossfade. They can all run at the same time and stuff. That's what I thought. These kind of structures are called perfect binary trees in computer science, which is when all of the nodes have exactly 2 children except of the leaf nodes that are at the end of the binary tree. Often used in search algorithms, I think. So here we are in the outtakes part of my code where I saved some of the older LFO code in order to show it for the video. And here is the LFO code with the crossfades hierarchy. And the reason why it's in the outtakes part of my code base is because it's not the approach that I still use. And I will talk about the actual approach soon too, but I think you will find this interesting. Here you can see commented out the basic LFO, and it still works a bit like this. It really just has these basic functions like setting the phase and setting the speed and stuff like that, synthesizing the phase, nothing too special. Then I have a struct for the X fade, which defines how a crossfade works. And then it's getting interesting. Here I have LFO X fades speed, and this was basically one of the higher level LFOs, which contains an array of lower level LFOs and always crossfaded if it wasn't already crossfading whenever a change in speed occurred, and then yeah, initialized a crossfade. And then if we scroll a little deeper, we see there is LFO X fades playhead jump, which always X fades when there was a jump in playhead, which means a loop. And as you can see, it has an array of the X fade speed LFO. So this is exactly what I described before with the perfect binary tree. Here we have LFO X fades on playback start or stop, and the final LFO that just has the most high level LFO that I wrote before. And yeah, that was just a terrible idea, to be honest. Whenever I had a bug, I could not really figure out which LFO caused it, or even a combination of LFOs, because when there was crossfade on one of these layers of hierarchies, it could just move everything to LFOs that haven't been used for a long time, and kinda hard to guess what their state was at that moment. And that made me really sad because I couldn't come up with a better solution, to be honest. I almost thought I had to give up on the idea of using crossfades at all. But then I remembered Abyss by DAW and I. I was beta testing this ambient synthesizer before it was released, and one thing that I noticed during my first test was scrolling through these sound color blobs sounded very grainy. I reported this to Peter, the developer, and he told me that he wants to solve it. A few days later, he told me about the issues that he had with this. He decided to take a crossfading approach, and he told me that it's not exactly easy. I remembered this conversation, so I decided to ask him again what his findings are and how he would solve my LFO problem. And he told me I should probably make a Crossfade Mixer. So here I made a little slide on my PowerPoint presentation about how my X-Fade Mixer now works. The X-Fade Mixer has a certain amount of LFOs. They are just sitting next to each other equally without any hierarchy. In this case, it's just 3 LFOs. And that's also the number of LFOs that I went with in the actual implementation, by the way. So as you can see, it's much less LFOs and it's easier to handle as well. In this example, the index is currently on 0. That's the index of the mixer. The mixer always knows which is the track that currently has the most recent LFO, and it has a 100% gain value, while the other ones have 0%, which means they are inactive and silent. Now it might be that a rate, BPM or PPQ change occurs, and that would initialize a crossfade, which means that the index value now moves to the next LFO, and now there are new target gain values for some of the LFOs. LFO 0, for example, now wants to go down to the gain value 0 from its maximum value down, while LFO 1 wants to go up to the maximum value. Now we are kind of half in with the crossfade, and this one went a little bit down, this one went a little bit up, but suddenly there is another crossfade because another rate BPM or PPQ change occurred, and that means the index moves on and this target value now goes down to 0, even though this thing hasn't even reached 1 yet, and this one is now on 1. And now these two things move down. I think it would have made more sense if both of them were now at 0, but whatever. So these just keep on moving down. They can still fade out. You could still hear them if it was an audio signal. And this one goes up. And now we have a little bit of a problem here, at least if we actually run out of crossfades and still want to initialize another crossfade. Because if there was another crossfade now, you could imagine that this index value would jump back to 0, even though this thing hasn't even reached 0 yet. So we would replace the LFO with the new phase and create a discontinuity while setting this target gain value back to 1. So if we had a lot of crossfades after another and it would be too much, then we would see that. Always just have to make sure that the amount of LFOs is the amount of possible crossfades at the same time plus 1. As long as that is the case, it will just work perfectly fine and you will never run into discontinuities. It's finally time to get to the bottom of it. I show you the code of the LFO and the procedural LFO and of the Crossfade Mixer. Starting with the LFO. The LFO basically just owns a phasor. A phasor just synthesizes a sawtooth wave between 0 and 1, updating the phasor, checking if the speed has to change, updating the speed. In the processing function, I synthesize the phasor and then process the wavetables onto it. Synthesizing the phasor is pretty straightforward. I'm just mixing the output of the phase with the phase offset parameter. And if this is a stereo track and there is some width on the width parameter, that also has to be added. And processing the wavetables just means to pick up the wavetable position info parameter and the buffer that currently holds the phasor. I will not go into detail now how a wavetable works because it's basically just a glorified array, so you can figure that out yourself, or I make a different video, I don't know. So let's look at the LFO procedural now. Here you can already see some really important decisions, like I decided that the X fade length in milliseconds is 200. That sounds fairly long, but it actually feels just right to me. You've seen in the Vital LFO that changes still seemed pretty instantaneous, not as bad as in Bitwig's sync retrigger mode, but still pretty grainy. And yeah, I just decided that I don't want that and chose a longer length, and 200 seems really good. Now I chose 3 LFOs for the Crossfade Mixer as well as the array of LFOs. These have to match. I will go into the reason later. Now it's getting interesting with the processing function. First of all, I calculate the parameter smoothing for the phase value, the width value and the wavetable position value. I'm updating the LFO, which means updating the position, the speed and whether or not it should crossfade. And then we start synthesizing the LFO by choosing the first track, getting the samples out of there. I just decided that the third channel of this buffer is always to synthesize the gain values of this mixer. And then I'm processing the LFO into the first 2 channels of this, or the first 1 channel if it's mono, and then I copy it into the samples array that is also output of this whole method. Or if the track is not active right now, I just clear the samples to make room for whatever comes next. So now I'm looping from the second until the last LFO. Here I'm doing basically the same things, except that I at the end add to the samples instead of copying, because obviously we don't want to overwrite what's already there, but just add to it so that it's a parallel processing setup. You're probably more interested in update LFO though, so let's look at that. Update LFO, fairly easy. I'm updating the speed. In update speed there can be an X fade trigger. If transport is currently playing, then I'm also updating the position, and else I'm not doing that, because as discussed before, no matter if we have tempo sync or hertz values, if there is no playback then it should just free run. Position only has to be updated when a change occurs or synchronization is beneficial, and else it will just do its thing and still move on, because the LFO just keeps on moving whenever you synthesize it. By the way, this position estimate value here, that is for checking if there is a loop. This basically means where would you estimate the next position to be. This is an int64, and the reason for that is because times in samples is also an int64. So when there is no playback, then the estimate is just times time in samples itself because it will stay where it is, and else the estimate is plus num samples, and you also have to consider the oversampling factor if the LFO is in some part of the code where there is oversampling right now. This is the case in this plugin. So let's check out update speed. In update speed I make a lot of temporary values which I always call n something because n is new BPS, new quarter node length, new increment value that's differently calculated whether this is temposync or not. And yeah, the calculation is still the same as before, but now there is the big if statement that decides if a crossfade is needed. The idea is basically either this is currently looping, which would trigger a crossfade, or, and then there is this big term, so all this, which means that there is currently a change in speed and also we are not still fading. So a loop can always trigger a crossfade, but change in speed can only trigger a crossfade if there is not a crossfade yet, and else the LFO has to wait some blocks until it can update the speed, which is not a problem because it will be sent the same values over and over again anyway. And this line is basically the reason why I know that I only need 3 LFOs, because I have maximally 2 crossfades at the same time. That's how I make sure of this logic. Well, and then it triggers the initxFade method, which just takes all of these temporary values and put them into the member variables so that they can be used later in the position function. And I initialize a crossfade and I tell the LFO with a new mixer index that the speed needs to be updated. The other LFOs can just keep their speed and will free run while fading out. Now let's look at update position. This is basically also a function where you have to make a distinction between temposync and not. You can disregard this whole latency stuff if your plugin doesn't have latency at this part of the DSP code. You can imagine if there was no latency now, which would mean 0 latency, so 0 divided by something that is 0, so PPQ position minus 0 is just PPQ position. So if you have no latency, just delete this. As you have already seen before, LFO phase incorporates the PPQ position, the BPS and the rate in hertz. And then you just have to update the LFO with that by making sure this is a fractional value between 0 and 1. Here we have the functions that check if the speed has changed. I don't think I have to explain that. Maybe a bit more interesting is the isLooping function, which checks for the current error in the estimation by taking the time in samples that we're currently at and subtracting the position estimate from it, and that way we can find out, okay, the error is bigger than 1, so this is definitely currently a loop and not just a normal playback. If you enjoy my content and you wanna support me actively, you can donate some money via PayPal or even show your appreciation by giving me monthly support via Patreon. More money means more content and better content. So now you basically know how the procedural LFO works already, but you probably wanna know what the xFade is like as well. So this is my xFade namespace, and here we have the old xFade that I used in my last implementation, where I just xFaded between 2 lower level objects and a high level objects to make this hierarchy thing. And yeah, I will not go into that because it was not a good idea anyway. So the Crossfade Mixer is a templated class that wants to know the number of tracks and whether or not it should be smoothing over the course of the crossfading, which I do, yes. The Crossfade Mixer has an audio buffer and an array of tracks and the current index. As you already saw before in my super professional looking PowerPoint presentation, the index always represents the current track that holds the most recent LFO. But as you can see, the tracks themselves don't even know what an LFO is. So I wrote this to be generic so that it can be used with other contexts as well. And I hope that this is true. You can never really know without testing. Preparing means resizing the buffer to 3 channels per track. The increment value, I just decided that all of the tracks have the same increment value, which is the length in milliseconds that is provided here. Boom. Then here is the init function. You have seen it before in the LFO. This initializes a new crossfade, which means the index is incrementing and then wrapped around num tracks. And then all of the tracks are disabled, but only the one that is selected is enabled. Here's a little trick that you might want to use yourself. You might not want to use this in a context like this, but wherever you want. We have a getSamples method here, and the input argument I means which track it should be returning. But you know that all of the tracks are in this buffer. So this buffer represents the audio buffers of all of the tracks all together, as you've seen in the prepare method, where I set the size of all the tracks here. And you might wonder, how can you get a specific 2-dimensional pointer out of that? Because this is supposed to return a double asterisk const asterisk. And you know, usually what you would do is just say get array of right pointers. and this would just return the entire thing. So let's check out what this does. So this is a two-dimensional double array, so we could return this, but it is not at the right position. So what we do then is say I times 3, because we have 3 channels per track. And what will it return then? Then it just returns a one-dimensional array, and because of that you have to reference it back into a two-dimensional thing so that it gets the other layer of this array. That's how you can get a specific part of a buffer out of a buffer. Very nice trick. I didn't know that it works for a long time, so maybe some of you also find it helpful. Now let's look at the tracks instead. So each track has a gain, which is the actual gain value, a destination gain, which is where it wants to go, an increment value, the speed of how it goes there, and it knows if it's currently fading. Disabling just destination gain 0, enabling just destination gain 1. If it's enabled, then that means that both the gain and the destination gain together is not 0, so one of them has still to be active. And if it's currently fading, then the destination gain is just not the gain. Now the synthesize gain values method, if we're currently not fading, then we're just filling the entire buffer with our gain value, and else we're setting the fading value to true, and we synthesize the gain values internally and then we smoothen them. Synthesizing the gain values internally just means we either have a destination gain of 1 or we have a destination gain of 0, and then we loop over all of the samples and then we let our gain value go towards the given value. And yeah, if it has reached that value, then we are just filling the rest of the values in here. My smoothing function just looks like this. I'm just using a generic cosine function to make it have smooth transition. There you have it. This is my procedural deterministic LFO, no matter if temposync or hertz. Hertz-based LFOs are usually non-deterministic, but they don't have to be, as you can see. And if they are not, then this solves the problem of inconsistent loops. It's better for finishing tracks with perfection, while keeping the natural off-grid LFO tempos in the project, and not having to resort to the gritty temposync values. Of course, this solution mildly complicates what people usually think of LFOs. It needs a lot of tweaking with the crossfade length and stuff like that, has a lot of subjective things to it, but it also enables a unique musical workflow, and I think it should be done more often. Because if I had personally taken part in this poll, I would have chosen the temposync values if I didn't know my new LFO, because that's something that always bugged me, that I cannot use a hertz-based LFO without feeling that it's kinda dirty and unfinished at all times. Alright, thanks for watching my new video. Like and subscribe, share it with all of your developer homies. And if you're interested in more topics about consistency, but this time not between hertz and temposync LFOs, stay tuned for the next video, which will be in some corner of this video. And it's about adding more consistency between standalone and plugin builds when developing plugins. See you next time.